Okay, so I would like to thank the organizers for the invitation. So the topic of my lectures is periodic families of automorphic representations. And so I'm going to start by an example. So what is a periodic family? It's a collection of modular forms, eigenforms, for various weights, infinitely many weights, and such that the map K gives Fk is continuous for the periodic topology. So, which means that we need to embed K in a set of weights that I will call periodic weights. And Fk is going to belong to a periodic space, which could be what we call a space of periodic modular forms. Or something more concrete like a space of periodic Q expansions or periodic Q expansions. So the first example of such a family is a remark of Serre in the 70s. And it's related to the theory of Eisenstein series. So if you consider an even integer k, and you know that there is an Eisenstein series of weight k for k greater than 2, such that the Q expansion is given by, so the constant term is a Riemann zeta function evaluated at 1 minus k, and the Fourier coefficients are given by Qn, n equals 1 to infinity. So here Q is exponential to I pi tau, with tau is in the Poincaré upper half plane. And here sigma k minus 1 n is given by the sum of k minus 1 power of d for d, the divisor of n. So Serre remarked that if you look at Ek of Q minus Ek of Q minus Pk minus 1 Ek of Q to P, then what you get is, so you remove one Euler factor at P for the constant term. And here you have C minus 1k P Qn. And here where this sum is the same sum, but where you restrict the sum here with a divisor of n which are prime to P. So this is the sum for d k minus 1 for d divided n d prime to P. So this is well known that if you have k which is congruent to k prime modulo p to the m, and if you have also k which is congruent to k prime modulo p minus 1, then dk minus 1 is going to be congruent to dk prime minus 1 modulo p to the m. And so in that sense, when we say that k and k prime are periodically are close periodically, we mean those two type of congruences, and then that implies that the Fourier coefficients, at least for positive n's, are also close periodically. And so for this term, it happens that it's true also, but it's more complicated to show. And actually, it's the same congruences for the constant m is actually a consequence of the Q expansion principle. So here this operation here is necessary because you see that if you just look at the Fourier coefficient at P here, what you get is 1 plus P to the k minus 1. And the 1 plus P to the k minus 1 cannot be a periodic function of k, a continuous periodic function of k. So in particular, so you see that, so this Eisenstein series here we call ordinary, has the eigenvalue 1 for the UP operator. So for the Atkin UP operator, which is the Weyk operator attached to the double class gamma 0p, 1, 0, 0p, gamma 0p. So gamma 0p is a congruent subgroup of SL2Z of congruences which are triangular modular p. So this operator has an important role here in this theory. And in general, if we take F a modular form, we say that it is ordinary if when you look at the action of the UP operator on it, what you get is you have an eigenvalue which is of periodic norm equals to 1. And so this is the case for this Eisenstein series. And so Serre raised the question of knowing if there exist other families of this type when one does not start from an Eisenstein series. And so a few years later, this question has been answered by Hida. So in the 80s, the early 80s, and the answer is yes. There are such families, provided that the form we start from is ordinary. So 4 ordinary forms. So the way that Hida proves this result is he constructed. So let's give some notation. Let's lambda the Iwasawa algebra. So take the formal power series in one variable, its coefficient in ZP. And so let's write, well, no, I don't need a notation for that. So let's, for an integer k, let's p k, the ideal generated by 1 plus t minus 1 plus p to the power k. So Hida showed that for any residue class A modulo p minus 1, there is a space S A, which is a free module over lambda, and such that SA modulo pk is actually isomorphic to the space sk odd of gamma 0p. So if k is congruent to A mod p minus 1. So here sk odd of gamma 0p is a space of Kuss form. So this is a space of ordinary Kuss forms of weight k, and which are ordinary, yes, ordinary Kuss form of weight k. And so the main point here is that this space SA is free over lambda. And moreover, there is an action of the Hecke algebra on this space, on the space SA. And so if you look at the algebra generated by those Hecke operators, so they form a commutative algebra, which is actually, it can be shown that it's dual, a lambda dual to SA, and therefore which is also free over lambda. And if you take now the spectrum of this Hecke algebra, then that gives exactly the families of Kuss form that I was wondering about. So here the main hypothesis is that the space here of modular forms are the modular forms here are ordinary. And so in the 90s, Coleman generalized this to finite slope modular forms. In the 90s. So the general finite slope case. So what is the slope? So if lambda is the eigenvalue of the UP operator acting on the modular form F, the slope of F is just given by the periodic valuation of lambda. And so therefore, finite slope is just saying that this eigenvalue is non-zero. And so the method of Coleman is a bit similar, but there is an important restriction, is that it cannot work with all weights at the same time. And so for that, it's convenient to introduce the weight space now. So weight space is a rigid analytic space over QP such that if you take a finite extension of QPL, then the L points of W are just given by the continuous homomorphism of ZP cross into L cross. And so if you decompose ZP cross as mu P minus 1 cross 1 plus P ZP, you see easily that you can interpret this as a disjoint union on open unit ball. And that gives this the structure of rigid analytic space. And so for each A, so the integer A here is just given by one ball, gives one ball of weight space, and there is P minus 1 ball. And lambda is isomorphic to the ring of rigid analytic function on this open unit disk, which are bounded by 1. So here, really, IDA can work on the whole weight space. So in Coleman theory, so he needs to restrict to affinoid subdomain. So he you start from a weight K, and then you find an affinoid neighborhood of this weight. This is seen as a weight by saying that, so this is a weight K, so bracket K here, which means that this isomorphism T gives T to decay. So you can always, so what Coleman proved is that if you take a weight K and a modular form of that weight, which is finite slope, then you can find an affinoid neighborhood of this weight, and you can find a formal Q expansion So where the ANs are analytic functions on this affinoid. And so when you evaluate now, so the analytic functions at weights which are in U, then you get a formal Q expansion with periodic coefficient, and this formal Q expansion has to be the Q expansion of modular forms. Well, I am a bit cheating here, but basically this is what it proves. And Coleman and Mazur succeeded to actually patch whole source families in a global object that exists in Hida theory, but that didn't exist in original Coleman theory. To obtain an analytic space, which is they call the eigencurve. So the eigencurve is a rigid analytic curve that sits over the weight space. And so the points of the eigencurve are in bijection with overconvergent modular forms. Of weight Wx, where Wx is a projection on weight space of the point. And so when the weight is an integer, it's clear what it means to be an overconvergent modular forms. And so in general, the way they define it is that they divide the Q expansion, the formal Q expansion, by the Q expansion of an Eisenstein series, an ordinary Eisenstein series of that weight, which we know that exists by the Serre example. And they get then a Q expansion, and they just say that this is a Q expansion of an overconvergent functions on the modular curve. So that's their construction. And so what they prove is that this eigencurve is equidimensional. And so each irreducible component of this curve gives a family of modular forms. So already for GL2, there are many applications of this kind of this theory. I mean, in the ordinary case, there is one application is a proof by Wiles of the main conjecture that clarifies the original proof by Mazur-Wiles. And therefore so there are other applications, but it was already clear that generalization of these two other groups was an interesting question. So I'm going to speak about generalization now. So let's fix some basic notation. So I'm going to take G a reductive group. And so I'm going to assume for simplicity that the center Z is split over Q. So over Q. I'm going to assume that G over QP is also split. And then I will define a model, Chevalier model over ZP. And then I define a Borel pair. And so I'm going to call I the Ivary subgroup. attached to this pair. And in that case, weight space is going to be the Regini analytic space such that the L points are given by the homomorphism of T of ZP into cross. Take the continuous homomorphism, and it's going to be a disjoint union of polydisk. And so if Z is not split over Q, then one has to divide the T of ZP by the closure of the center. Okay. So in Coleman IDA series, the UP operator played an important role. Here we have similar operators. So the way to define them are the following. So we consider T plus the element in T of QP such that T inverse N of ZP T are included in N of ZP. So N is just the unipotent radical of U. And one even denote T plus plus the element in T plus that contracts completely this unipotent radical, which means that intersection of T minus N of ZP Tn is just reduced to 1. And so I didn't say that in the case of, in the classical theory, the UP operator is a compact operator on the space of overconvergent forms. And in that case, the echo operators U sub T given by the double class ITI are going to be also compact operators on certain spaces. And this is a spectral theory of those operators that play the role of UP here. Okay. So that defines the echo operator at P. So one has to define the spaces now. So of course, one possible generalization of this is to consider Shimura variety and consider automorphic sheaves on the Shimura varieties, and then define the ordinary locus and then strict neighborhood of the ordinary locus, and then define overconvergent modular forms in that setting. And that gives a good theory that has been developing a lot recently, but that gives account only on for groups that give Shimura varieties. And for other groups, it's also interesting actually to study this. So I'm going to fix K sub P, an open compact subgroup of the finite Adler waveform P. And then I'm going to consider HKP. P is going to be, so I'm going to denote curly P, UP, the echo algebra generated by those UT. I mean, this is a commutative algebra. It's not difficult to see that. If you compose UT and UT prime, then this is UT times T prime. And then you consider this echo algebra, which is UP tensor. Then you take the compactly supported function on G of AF away from P, which are bi-invariant by KP. And so we are going to define, so if we have a module M on some subgroup or submoduloid of the finite adels, one can define a local system m tilde on SG KPI, which is a locally symmetric space so here we divide by k infinity, we have to divide by the center, the infinity, and then KPI. And so what we want to do is to study the action of this Eque algebra on the cohomology of this local system. So the question is, which local system are we going to take to construct families? So what we want to do is to construct a family of local systems that vary analytically with the weight. And so one way to do this is to consider locally analytic induction. And this is an idea which goes back to the work of Ash and Stevens. And actually, it also goes back to Hida, because in some of his work, he considers continuous inductions also. So here we are going to take lambda, a weight. So this is a continuous homomorphism from T of TZP to L cross. And then it's not difficult to see that forces this homomorphism to be locally analytic. So lambda is going to be locally analytic. And then when consider A lambda of L, or A lambda, this is just the space of locally analytic function from I into L such that f of T n minus G is equal to lambda of T f of G. So for T inside T of ZP and n minus inside the opposite unipotent to n minus of ZP, section I. And so as a space of function, by this condition and using the decomposition of I as n minus intersection I times C of ZP times n, you see that as a space, this is isomorphic to the space of just analytic function on n of ZP. And this space itself does not depend on lambda. But so here we have an action of I on this space just by right translation on the argument. And so which means that we have an action of I on this space, which depends on lambda. But only the action depends on lambda. So we consider d lambda the continuous L dual of A lambda. And so this is what we call a space of periodic distribution. And so what we do is that we consider the cohomology of AG KPI with this system of coefficients. So then there are several questions. the topological equation. So this space A lambda, so is an inductive limit of p-adic Banach spaces. So you can consider A lambda n, which are the space of functions which are analytic of disk of radius p minus n. And then this AN is going to be a Banach space. And so you can therefore see A lambda as an inductive limit of Banach spaces. And actually, the inclusions are compact maps for the topology. And therefore, you can see that D lambda is what we call a compact Frechet space, which is a projective limit of Banach spaces with compact transition maps. So compact Frechet. And so what you can check is that you have also an action of T plus acts on A lambda, and therefore by duality on D lambda. And so you can check that if you take an element in T plus plus, then so this this action improve the radius of convergence of the analytic function. So therefore, now when you restrict the analytic function, so you apply this T, you get something which is convergent on larger disk, and then you restrict to the original disk, and this restriction map is a compact operator. So therefore, you get that this T plus plus act on A lambda as a compact operator. And by duality, it acts also on D lambda by compact operators. So therefore, here we have that the UTs acting on this space would be compact operators if we can show that this space is a Frechet space or but so it's not clear that it is, because what we do is that we take cohomology here, and we don't know that when you look at the complex defining this cohomology, it's not clear that the maps are the image of the differential gives closed subspace, and therefore when you take the cohomology, you can get something which is not Hausdorff, and so moreover you may have this topological problem. However, what can be done is that using the Borel-Serre compactification, it's possible to, so you consider the Borel-Serre compactification. The cohomology of the Borel-Serre compactification is the same as the cohomology of this quotient here. And therefore, it computes also the same cohomology. So if you take a finite triangulation of this Borel-Serre compactification, you can see that you can construct actually resolution that are finite lengths and projective, and that computes this cohomology. And in particular, you can define the Hecke operators at the level of this complex and show that those operators are compact at the level of this complex. And now those complex are basically given by finitely many copies of the D lambda, and therefore you have a compact action on the UT of the terms of this complex. And therefore, at the level of the complex, you have a spectral decomposition. And so what you can do is that you can look at the finite slope part of the complex and then compute the cohomology of this finite slope part. And that makes sense, and what we get is the finite slope cohomology. So this is slope part. So this is perfectly well defined now, and we have the following definition. So we said that if we have sigma, an irreducible representation of H of Kp, so which is this equialgebra here, which says it is finite slope, it is automorphic and finite slope, and finite slope if it appears in such cohomology. So I'm just going to write like this. And so the question is that if we consider the set of all irreducible automorphic finite slope representation, we can ask ourselves has this set a structure of rigid analytic variety? And so we can ask what is its dimension and other geometrical question. So the answer to the first question is yes. So the space, the set of automorphic finite slope representation, so according to this definition, has a structure of rigid analytic space. So to simplify the exposition, instead of taking the whole equialgebra, I'm just going to concentrate with the equialgebra, the spherical part of the equialgebra. And so if I call S the finite set of prime where Kp is not spherical, then we can look at RSP, which is going to be take just the spherical equialgebra away from S and P. And then, of course, you keep the UP operators, the UT operators. And so this is a commutative algebra. Actually, it even belongs in the center of this one. And therefore, when you have a sigma, then you have a theta sigma, which is a character of this algebra, which gives the eigenvalues of the spherical equioperators. And so there is a result, which is mainly due to Ash and Stevens, is that so there exists a rigid analytic variety, let's say E, sitting over the white space. And so you can think of this as inside spec RSP or W. So elements in here are just pairs of a character of this algebra and a weight. And this point belongs to the rigid variety E if only if theta shows up in in the cohomology of d lambda. Yes? So the question is, so this result is interesting, but it raises a lot of questions. So what are the dimensions of the reducible components? So do we have questions? So one question is, so what are the dimensions of irreducible components? Yeah, something that comes from their work also is that the dimension of the reducible components are smaller than the dimension of weight space. This is from. So, but we can ask, are there components of the same dimension? If there are components of the same dimension, are all of them of the same dimension? It's not clear. So another question that one can ask is, in case where the dimension is not maximal, which is the dimension of weight space, are the classical points dense in the components? So are classical points dense in components? So as it is the case for GL2. So what is a classical point? Maybe I should mention that. So I have defined L lambda as this space of locally analytic function. And of course, it contains a locally algebraic function, which is a induction from B minus to G of lambda, algebraic, and you take the tensor with the locally constant function on the vary. So this is what I call V lambda. So this is the irreducible algebraic representation of highest weight lambda, and so it sits in A lambda. And so one thing that comes in that theory is that we want also to compare the cohomology of this space, of this representation, or its dual with the cohomology of D lambda. So we have, of course, a map, a surjective map like this, and actually it's possible to complete this surjective map into a resolution, which is a locally analytic version of the BGG resolution. And so we have analytic BGG resolution. And that gives a way to compare the cohomology of V lambda dual and the cohomology of D lambda. And so if theta is a system of eigenvalues here, which is non-critical with respect to lambda, lambda being an algebraic weight now, of course, in that case also, lambda has to be algebraic, of course, algebraic dominant. So what does that mean? Here, that means that the periodic valuation of the eigenvalues of ut are not too large with respect to lambda. And that can be made precise, but I don't have time. And so when we assume this, and then we take the theta eigenspace of d lambda, then this is morphic to the cohomology of the generalized theta eigenspace of V lambda dual. And therefore, in that case, it makes sense to say that a point is classical, which means a point theta is going to be classical if it shows up here, and therefore here. And in that case, it is attached to a classical automorphic representation. So I have given a partial answer to question 1, and also a conjecture I would like to state now. So the partial answer is first the following. So I'm going to call MQ dagger theta lambda the dimension of this HQ d lambda theta eigenspace. So the multiplicity of this theta here. And then I'm going to call M Euler-Poincaré dagger theta lambda the alternating sum. And so the theorem that gives a partial answer is that there exists a subvariety inside the eigenvariety that I call EP, such that so a point x, x lambda x, belongs to EP if and only if well the Euler-Poincaré characteristic of the x lambda x doesn't vanish. So, and moreover, EEP is equidimensional. Of dimension, the dimension of weight space. So in particular, so if you apply this to GL2, you recover the construction of Coleman-Maser eigencurve. But you can also apply this result to any group G such that G of R has discrete series, because in that case, you can see that the cuspidal representation attached to this, of this group with a regular weight shows up only in the middle dimension, and therefore the Euler characteristic is always non-trivial. I mean, the classical Euler characteristic. And if the weight, if the slope is not too large, we have this isomorphism that tells that this Euler-Poincaré is non-trivial. So therefore, this subvariety contains all the classical points of regular weight, at least, cuspidal regular weight. Okay, so this is a partial answer because we can expect that there are. Oh yes, and of course, if the group has no discrete series, then this statement is basically empty because in that case, the Euler-Poincaré characteristic is always 0. So in particular for GLN, n bigger than 2, we don't expect to have components of maximal dimension. And so for, in general, there is the following conjecture. So let's take a point x in the eigenvariety and assume that there exists a unique irreducible component containing X. Then there exists an interval AB of integers such that the multiplicity MQ dagger theta lambda is equal to, or there exists an interval integer AB and some integer M depending also of X on X, so that this is equal to the binomial coefficient B minus A Q minus A times MX. And the dimension of the component, well, sorry, I prefer to say the codimension of the projection onto X of the component is exactly B minus A. So in particular, that say that the dimension is maximal if only if there is, you see that this formula tells you that the multiplicity vanishes outside the interval AB and is given by a multiple of some binomial coefficient. And so if A is equal to B, then we have maximal dimension. And if B is equal to A plus 1, we should have codimension 1. And actually, those two cases can be proved. There is a student of H, David Hansen, who proved this case for GL2 over an imaginary quadratic field and for GL3 over Q. But there is also an evidence for this is that, so the evidence is that, well, so first, it's not difficult to show that B minus A is bigger than the codimension. And so this is a.
So that's the codimension projection.
Yeah. So this is. Yes. Yes. So if B equals A, that means codimension 0. And therefore, we have the component of maximal dimension. And if B minus A is equal to 1, the codimension is at most 1. And it cannot be 0 in many cases because we can see the support is torsion. And so therefore, we can see that it's codimension 1 when B minus 1 is equal to A, 1. So this is a simple argument to show that. So that means that there are families. And the conjecture is saying exactly that there are not too many.
No, but I mean, to say this, you need an a priori definition.
Excuse me?
Well, to say this, make the statement,
yes.
You need an a priori definition.
Yeah, so B is going to be the maximal degree where you have cohomology, and A is the minimal degree where you have cohomology. And you assume that you have cohomology in between. Okay. So another evidence is that, except the case GL2 over K on GL3, you have that if you apply this for SL2 over F a totally real field, and if you take theta, the system of Ecker eigenvalues of an Eisenstein series, ordinary Eisenstein series. So if you call D the degree of your totally real field, then you can compute the Eisenstein cohomology. And this has been done by Harder many years ago. And he proved that you have cohomology exactly in degree d plus 1 until 2d minus 1. And so in that case here, b minus a is just d minus 1. So on weight space here is exactly dimension d. So therefore, that the conjectures say that the dimension of the family of Eisenstein class should be 1. But this family is dimension 1 plus delta, whereas delta is Leopold effect. So the conjecture say that it implies that the family is dimension 1. And this is equivalent to Leopold for F and P. So this conjecture somehow, from this case, you can interpret it as a non-abelian generalization of Leopold. Okay, so I don't have time to give application of this series. So I'm going to just say a conjectural answer to this question, at least for so there is a conjecture of Ash, Pollack, and Stevens, and their conjecture is that if you start from, so it's for GLN. Let's say GLN. I mean, they state their conjecture for GL3 over Q, but you can generalize it easily to GLN n bigger than 2. They conjecture that if you start, so in that case, weight space is dimension 3, and so if you look at the classical points, for a classical point, the weight has to be self-dual, and therefore the dimension of the self-dual weight is 2. Dimension self-dual weights. On the other hand, for GL3, you have cohomology in degree. So you have cuspidal cohomology exactly in degree 2 and 3. So therefore, if this conjecture, I mean, is true, which is true in that case, the projection on weight space dimension is codimension 1, so therefore the families are dimension 2. So that coincides well with this situation. But so their conjectures say that if you start from a classical point, then the family, I mean the irreducible component containing this classical point contains the Zariski-Dunn set of classical points if and only if the original representation is self-dual. So if you take theta, classical, I mean, take x equals theta lambda classical, so let's call that x the component of the eigenvariety containing that point. We know it has to be dimension 2. And so this contains a Zariski-Dense set of classical points if and only if theta is self-dual. And so it's not difficult to show that if theta is self-dual, then the component containing it contains the Zariski-Dense set of classical points. I mean, there are several ways to prove this. Either you switch to a unitary group, or you you make a twisted version of the Euler characteristic Poincare argument that I made. And, but this direction seems very difficult. And I don't think anyone has any idea. So there is a relatively, there is a similar conjecture for GL2 of an imaginary quadratic field, which has been investigated by Maser and Caligari in the case of Galois representation, and which is quite similar. And it seems that it's related to some general Leopold conjecture. And it's, I don't know, maybe it's why those two conjectures may not be completely unrelated. Okay, I'm going to stop here.
You mentioned two ways of proving the existence of this heuristic lens. Sorry.
Yes. I mean, that was following one of your suggestions. So, because in that case, when you do the Euler-Poincare characteristic argument for GLN, then the Euler-Poincare characteristic of the GK comma G vanishes because you have no discrete series. But if you twist it by an involution of Cartan type, you know that this comma G doesn't vanish. But then you need to find an automorphism of GLN, which is now a global object that is the Cartan involution at infinity, I mean, of Cartan type at infinity. And there is the obvious involution of GLN. But when you do that, you capture only the self-dual representation. So then using this argument, you can show that you have a family of self-dual representation.
Other questions?
Hello. Anyway, important to remember, tomorrow we start at 9:30, not at 10, at 9:30.